Start.
Yes.
Okay.
So I'm very happy to speak to you from the place where I live, which is Ithaca, New York. Of course, where I come from is closer to you, and I was born in what was then Poland, but now is the Ukraine, in Zolochiv. And we can talk a little bit about my path in science and my biography at the end of the lecture. But I think it's important in these difficult times for Ukraine and for the world, but especially for you, to in fact try to talk about science, because we must not lose fact that underneath everything there is our desire, our ambition, our quest for gaining knowledge of the world around us and within us. And I would like to tell you about some chemistry. And the chemistry that I will tell you about is chemistry that is extremely unlikely, from my experience, to have entered your education. The reason for that is it's most of it quite recent. And second, it is at a meeting ground of chemistry and physics. And third, it's just has not entered textbooks at all. And so it is something really new. This picture here, of course, comes from an Asterix comic book, but it is a simplistic picture of high pressure being applied by the Gauls to the Romans, the invaders there. But maybe it's in some way symbolic of Ukraine and Russia in its own way. I'm giving this picture because we have to smile even in difficult times. Now, let me tell you about the chemical imagination at work in very tight places. And every word in this title, by the end of this lecture, will have some meaning, and I will justify it. Let's talk first about pressure. So pressure is measured in units typically of, let's say, atmospheres, or bar is a more precise unit. But in the field in which we are working experimentally and theoretically, and this is going to be a talk about mainly theory, but with experiment very closely to it. The unit is a gigapascal. A pascal itself is a very small unit. And so the common unit in high pressure research is a gigapascal. A gigapascal is 10,000 bar, which is about 10,000 atmospheres. And that is a high pressure. It is much higher than what you pump up your bicycle to. It is actually higher than what is used in many industrial processes, like the Haber-Bosch process. To get a feeling for it, it'll come with time. But I can tell you that the pressure at the center of the Earth, which comes just from the gravitational pressure, the pressure at the center of the Earth is about 3.5 million atmospheres, which is about 350 gigapascals. And that's not a bad number to keep in mind, because as it happens, even though we cannot be at the center of the Earth, in the laboratory, my colleagues, people can reach pretty routinely pressures which are close to that. Around 200 gigapascals is very, approachable. Just to give you an idea in another way, on going from 1 atmosphere, 1/1000th of a gigapascal to that pressure at the center of the Earth, the volume of a block of solid methane, natural gas, which you know can be liquefied, or of lithium, or of any molecule, the volume decreases by a factor of about 5. So you have to imagine, and this is very hard to imagine, that there is Superman and he is squeezing this block, and its volume goes down by a factor of 5, or the cube root of that in any dimension. For an ionic solid like sodium chloride or water, which becomes ionic at high pressures, it's a factor of about 3. And for metals like iron or gold, which we do not think are compressible, in fact, under high pressures, they can be compressed and the volume goes down by a factor of about 1.7. Now, there is a place in chemistry and in chemical industry where high pressure is used routinely, and you study about it in an introductory course about why it is used. It is used to more readily attain equilibrium. And you can buy, if you are building a chemical factory for a few $1 million, you can buy a reactor which takes 100 liters, 1,000 liters, and compresses it to pressures. And the typical pressures in these, in the Haber-Bosch process, which I mentioned because it is the most successful industrial process on Earth. It is run in tremendous quantities to produce ammonia from nitrogen and hydrogen. The pressures involved there are, in that vessel, which you can buy, are 130 to 300 atmospheres. This is almost nothing compared to the pressures under which the experiments I will describe to you are. In fact, as a joke, the people who work in the high pressure realm refer to the industrial pressures, which cost so much to produce. They refer to them as near vacuum. It's all a matter of perspective, depending where you work. The way these high pressures are attained is in a variety of instruments. Let me see if I can get my pointer to work. No, I use the pointer here. The prime instrument is something called a diamond Anvil cell. And what's in that are 2 diamonds that you see in the left-handmost view that are polished flat. And then through a hole in a piece of metal, the 2 diamonds are pushed on each other. And then the whole thing is compressed. The basic cell, called the diamond anvil cell, can be held in your hand. It is then put in a hydraulic press, which is substantially bigger. But this cell can, together with a not very expensive pressure apparatus, can be used to generate pressures easily of 20 gigapascals, and with difficulty, as I said, go up to 200. You need a bigger apparatus like the one that you see, which is about 1 meter across. But the basic cell is something that can be held in your hand. And that is the workhorse of the high pressure community. There is another way to study high pressures. This is exemplified here by an American space capsule re-entering, and ahead of it, it creates a shock wave. That shock wave of compressed gas has in it very high pressures of the orders, again, of 100 rising to 1,000 gigapascals and higher. And here in the middle on the bottom is a piece of equipment in which lasers are fired in to produce fusion, producing a very high pressure in shock waves, which are generated in the middle of this apparatus. The thing that is different about shock waves from diamond anvil cells is in diamond anvil cells, in the small volume that is between the diamonds, that there is generated, that the pressure there is uniform, hydrostatic. But in a shock tube or a shock wave that is set up by, say, lasers being fired in, the pressure and the temperature both rise in what's called an isoentropic compression, so that the process is more dynamic, but you can still figure out something from it. So that's the experimental apparatus. If you want to read more about it, in the magazine Scientific American about 3 years ago, there is an article about the technique. What you see in that picture is in fact a diamond anvil cell. You see the hole in the middle, a diamond from above, there'll be a diamond from below, and in between is a space. And the reaction volume in a typical diamond anvil cell is maybe 1 millimeter cubed. You can get in a good amount of matter in terms of atoms or molecules in there, but it's not much. What you are doing in a typical chemical reaction, which I have been involved in these, the making of some threads of benzene polymer, what you're making in a typical experiment is 50 milligrams of the material. And now I'd like you to think about doing the analytical chemistry on 50 milligrams of some product. Under pressure, pressure is force per unit area. There is only one imperative for atoms and molecules. Nothing else matters as the pressure increases. And the imperative is get smaller. That is, and it's obvious, you're compressing. So what happens is you decrease your volume, you increase your density, which is the number of atoms or the mass per unit volume. Or to put it into colloquial English, the only imperative for atoms and molecules is to get closer together. They can't fly away. Okay. So now that's going to be very important. It also means that density, where there is a choice, supposing there's a choice of two materials, A and B, and they are the same thing. Of course, I think of diamond and graphite. When you have diamond and graphite, and the two are about equally stable, they're a little bit different. But when you have diamond here in its structure and graphite, which doesn't look as pretty as that, if you have the two structures and the density, and then you look at the densities of the two, and the density of graphite is 2.27 grams per centimeter, and diamond is much denser at 3.51 grams per centimeter. And now if someone asks you on a test, let's say, what's going to happen? Which one's going to be more stable at high pressure? They are about equally stable at normal pressure for reasons that are interesting by itself. But under high pressure, graphite doesn't have a chance because diamond is much denser, so that if you provide enough heat to pass over the activation barrier between the two, graphite will go into diamond. And that's the way, of course, the diamonds are formed in the mantle and then come up geologically through from the mantle, from the high pressure to atmospheric pressure, through something called kimberlite pipes, but that is more geology here. Anyway, diamonds can be made by high pressure. Let's take a few other things. The one thing I said is, under pressure, there's only one imperative: get closer together. So a gas is a luxury. The atoms are far apart. You can calculate how far apart on average the molecules of the air are, nitrogen and oxygen. And there's a lot of empty space. As you apply pressure, you will go to a liquid and eventually to a solid, the more dense form of the same material. Everything does this. This is, of course, sometimes it doesn't take much pressure. This is, of course, why natural gas is shipped in liquefied form, because it is a more denser form, which is easily available, can be restored to the gas. The other thing that happens to everything under sufficiently high pressure is under sufficiently high pressure, and sometimes it is under very, very high pressure, everything becomes metallic. Now, what's happening here is a consequence of the electronic structure. At normal pressure, many things are insulators. Translated into physics, chemistry, what that means, as you see in this graph at left, is that the filled levels of the material are separated by a gap, roughly the color of the material, from the unfilled levels. Now, as you compress things, the filled levels interact with each other, spread into a band, and the unfilled levels spread into a band too. And at some point, those bands will touch and cross. And that is when the material becomes metallic, when it's possible for an electron to jump to another place without much resistance. The progression is colorless to colored to metallic. And there are some interesting things which have been studied recently, that there are some materials that start out metallic that become insulating, but then eventually return to metallicity. But I don't have time to tell you about this. You can find out about that. Incredible things happen at high pressure, and this is part of the interest, both to physics and to chemistry in terms of properties. First of all, since I said anything can be metallized, can we metallize, I don't know, water? Can we metallize nitrogen, oxygen, hydrogen? So just to say things quickly, hydrogen is an interesting problem. I'll come back to it. It turns out that experimentally, helium has not been metallized. It would take the pressure at the center of a gas giant, such as some of the exoplanets we have, to metallize helium or neon. But xenon has been metallized experimentally. So I'd like you to imagine that. Xenon, a gas, condensing into xenon, a liquid, freezing as a solid, and then applying more pressure, becoming not just a transparent solid, but a metal. And that has been accomplished experimentally. Iodine can be metallized. Iodine is already colored. It doesn't have a big gap to cross. It doesn't take much to metallize iodine. Some ionic substances can be metallized relatively easy, and experiments have been done on cesium iodide and barium telluride, but sodium chloride has not been metallized in the laboratory yet. It would take pressures, again, in excess of what is available experimentally. Now, here are some of the more interesting things to chemists, and you can see why, and also some of the things we don't tell our students. CO2 and N2. So for our students, we generate a mystery. That's the way the world is. we tell them that CO2 is a gas and SiO2 is what it is, the structure of quartz, a solid with a framework of 4-coordinate silicon and 2-coordinate oxygen. But you know, silicon is under carbon in the periodic table, so isn't SiO2 supposed to be like CO2? Interesting problem. But as you apply pressure to CO2, it goes, everyone knows what happens to CO2 under pressure. It goes into a common laboratory material, which in English is called dry ice, and can be bought and is used for cooling things. And that's still a crystal of CO2 molecules, as you see it left. But if you apply more pressure, about 50 GPa, a form of CO2 develops that is pretty close to that of quartz. So it's possible to make that transformation. N2, which has the strongest diatomic bond of 10 eV, 230 kilocalories, to rip apart the N2 molecule, under very high pressure and with some heating, transforms into a 3-coordinate net whose structure is, or layered net, it's a little hard to see what it is, but what you can see very clearly there are 3-coordinate nitrogens, just like in a structure of phosphorus, arsenic, and antimony. So these are some of the interesting things that can happen. Then there are things that have been found that are just very unusual and for which there is no parallel. So CO2 and SiO2, there was a parallel, but now you can, under high pressure, make stoichiometries, and this is mostly theoretical work, but also some experimental work on one of them. You can make stoichiometries of Na and Cl, which are very different from what we have under normal conditions, which are just 1-to-1. You can make things as sodium-rich as Na3Cl and as chlorine-rich as NaCl7. Now, I should tell you right away, you can make them and you get the structure of these from X-ray diffraction, which can be done through the diamond. So I didn't tell you about what experimental techniques you can use to study a material in situ, under pressure. But you can, in fact, study a lot of things using X-rays. You can do Raman. You cannot do nuclear magnetic resonance. And there are other limitations on the techniques that you can use. You can make these materials, but the real question is, what happens when you reduce the pressure and you return to normal conditions? And whereas for graphite, which has turned into diamond, it remains as diamond. For these materials, which are so fascinating, NaCl7 and Na3Cl2, and I could tell you something about their structures. There are some pictures here, but we don't have time to look at it. These materials, when the pressure cell, the diamond anvil cell, is returned to normal pressure, they go back to NaCl and Na and Cl2 in whatever proportions are needed. These materials do not allow a stable return to ambient pressure. So it's too bad, because it will be interesting to study them, but we take what is given to us, which is the high pressure. Hydrogen has been the subject of some controversy for some time. Hydrogen, of course, is H2. There have been calculations on metallic hydrogen, as you see here, from 1935. It would take a pressure about that at the center of the Earth to make it metallic. And there have been claims of making it metallic. Under both pressure and temperature rise, there is a verifiable claim of that hydrogen has been metallized. My colleague Neil Ashcroft, who is no longer alive, who led me into the high pressure field, had an idea of chemical precompression for metallizing hydrogen. He thought that maybe you could make a gas of hydrogen atoms and then to prevent them from sort of falling down into H2, you could bond the hydrogen atoms to some other atoms. He called this chemical precompression, and then compress the whole thing. This has led to a lot of investigation in recent years of high hydrides of the elements. So people have tried to make materials which have a lot of hydrogen and something else. And here are two that have attracted a lot of interest. They are SH3 and LaH10. Now, the first thing to notice is everyone who is listening here knows that sulfur and hydrogen form a molecule, which is usually written as H2S, hydrogen sulfide, which doesn't smell well. Well, this is made from hydrogen sulfide plus some extra hydrogen, and they're compressed together, and you get a material whose structure is shown here, a very high symmetry structure at about 250 gigapascals. And it seems the composition SH3, not 2, but it was made from SH2. And this material, what's interesting about it is it is superconducting at 203 K. Another material prompted by Ashcroft's suggestion is a lanthanum hydride. The stable lanthanum hydride would be LaH3 or LaH2, since lanthanum is trivalent. But if you add extra hydrogen and compress it at high pressure, it seems you can make a framework of LaH10 in which there are polyhedra of hydrogen and lanthanum sitting in the middle of these polyhedra. And this material is superconducting at a still higher temperature, and recently has been found to be superconducting at ambient temperatures and even higher. So there's a lot of interest in these materials as possible superconductors, and a number of groups around the world are very active making high hydrides of the elements. If you want to read more about what happens at very high pressure, there is a review article we wrote early on, but it is directed toward chemists. Wojciech Kruchala, who is in Warsaw, and Neil Ashcroft and I, and a graduate student who is now in Beijing, Ji Feng. We have looked in general at what happens under very high pressure. And now I want to give you the sort of an outline of what happens to matter under high pressure in terms of a progression of things. So a kind of guideline. This is not a prediction of one particular thing, but of a general picture of the physics involved. There seems to be a hierarchy of responses to pressure in crystals. The hierarchy advances with increasing pressure. And I will go through these in part, because this is where gives us an idea of the overall picture. We will look at all of these. The first one is a complicated statement, penetrating the repulsive region of intermolecular potentials. So this has to do with molecules being compressed. Like if you have a crystal of benzene or of H2 and you compress it. So As you know, the interaction of two molecules is governed by what you see at left here, by potential energy curves, which are usually written as having, this is what's called the Lennard-Jones potential, typical thing for molecules. It has an attractive part that goes as 1 over r to the 6th, and it has a repulsive part that usually is written as 1 over, going as 1 over r to the 12th. The larger the molecule in terms of atomic weight, the more it has. The attractive part, for that is responsible the London dispersion forces. These are the fluctuations of electronic structure as two molecules approach each other. For the repulsive part, it's presumably the cores of the atoms bumping into each other. And together, they give you the structure. Here at right is the structure of the benzene molecule at ambient pressure. These molecules of benzene are almost indistinguishable from the molecules of benzene in the gas phase. We have crystal structures and we have electron diffraction gas structures. The benzene molecules in these are at about 3.2, 3.3 angstroms apart between the planes of the molecules. And that is about the packing distance in graphite. So that's the minimum over here. And it's the small attractions that push it into that minimum. The steepness of these curves is grossly deceptive in the sense that people think it goes up so quickly that it must cost a lot to penetrate this repulsive region of the van der Waals potential. But it doesn't, not for a while, because this energy scale is not written here, but this depth of this minimum, which is what forms the benzene crystal, is usually rather small. So the interaction, van der Waals interaction between two atoms is of the order of 2 kilocalories, a tenth of an EV. That's almost nothing. And so that it's easy to squeeze in. Let me give you an example from some calculations. This is the easiest way to show this. What I'm going to show you is theory, but the theory is calibrated by experiment here. In the first thing at left, I'm going to show you what happens when you take a silane molecule, SiH4, which is like CH4, like methane. Here is one. And you see these other things over here? Okay, those are not SiH molecules or an Si atom. Gold is silicon, green is hydrogen. No, that's 1 unit cell. And when you put the other H unit cell in this cubic structure, then you will regenerate a full SiH4 molecule. What I'm plotting here from calculation is not the nearest neighbor SiH distance, which remains as it is as a function of pressure, pretty much what it is at 1 atmosphere. But what I'm plotting here is the next nearest hydrogen-hydrogen distance. So that's the distance between the hydrogen of one SiH4 and the hydrogen of the next SiH4. And here it is as a function of pressure. And you see it starts at the 3.1. That's the van der Waals minimum for 2 silane molecules. And as I increase the pressure, that distance goes down, first precipitously so. I want you to notice what's happening here. This is in angstroms. This distance goes down 1 angstrom in the first 10 GPa. That's this distance. That's and that distance goes down 1 angstrom. Now, what I don't show you, but I should, is that the bonded SiH distance goes down by less than 100th of an angstrom. So there is at least a factor of 100 between the space loss between molecules relative to the squeezing within a molecule. Now, when you squeeze harder, the molecules eventually bump into each other, and then it's harder to compress them. That's what this part of the curve shows. Here is the same thing now over a scale of 500 GPa and 0 for the structure of H2. H2 in a crystal has H2 molecules. And incidentally here, this is a plane. You see this single atom, that's not a hydrogen atom. That's the top of an H2 molecule that's sticking up perpendicular to the plane. What I'm plotting here is, again, the second shortest HH distance. Why am I doing that? Because the shortest HH distance, which is 0.74 angstroms, the bond distance in the H2 molecule, changes again by less than 100th of an EV, goes up and down. And there are interesting reasons we have analyzed for it going up and down. It sometimes stretches, it sometimes contracts, but it never changes by more than 1%. Meanwhile, in the first 5 GPa almost of the pressure, the distance between H2 molecules goes down by 1 angstrom. Now you see what I mean by this statement, colloquial statement, van der Waals space is most easily compressed. This is what the first thing that happens when you squeeze. I show it for molecules, but it also happens for extended solids. The next regime that one enters is there is increasing coordination at main group and transition metal elements. So now I want you to, again, to get back to the general picture. Think of molecules. The molecules are under pressure. They have to come closer together. They're not allowed to get further apart. That's not in the rules. They must come closer together. And a certain amount of coming closer together is gained in the initial stages by squeezing the van der Waals space out. But after a while, the hydrogens or whatever is on one molecule comes closer to the main group of the other molecule. And so what you get is increasing coordination at main group and transition metal elements. This is what's going on, of course, in carbon dioxide going from a molecule to a quartz structure. It's what's going on in a nitrogen molecule going to a 3-coordinated net. Even though the bonding in the N2 molecule is so good, the triple bond of N2 is worth 10 EV, still it will give up the 2 pi bonds when you squeeze it together because it has no option. It has to go get closer together. And get closer together means form more bonds. Let's in this thing about getting closer together. Let's say it another way. Here's the metro in New York City. When there's few passengers, the density is low. People generally sit as far apart as possible. The average number of nearest neighbors is 0. You go, except if there are lovers, then the average number is 1. When you have more people, the average number of nearest neighbors in this seating arrangement is 2. Here at the bottom, you see what happens at what we call rush hour. It can get worse than this. This is the Tokyo subway. In the Tokyo subway, rather amusingly, people are hired to increase the pressure. The basic idea here is the sardine can principle. When you increase the pressure at a certain point, you must increase the coordination at the main group and transition metal elements. Let me show you one example of that. I told you silane. It forms a crystal of, this is calculations, of molecules. The van der Waals space is squeezed out. What happens next? It turns out that the SiH4 molecules penetrate, and the electron and the geometrical and electronic structure rearranges to a structure which, look at the right one. This is one we calculated, predicted. There are these, again, gold is silicon, green is hydrogen. I will describe the structure for you. It's easy to describe. There is a polyhedron called a dodecahedron of hydrogen atoms. At the center is a silicon. Each silicon shares one hydrogen with the other silicon. Here is one of these polyhedra taken away. And what you see is this silicon in the center is 8 coordinate, not 4 coordinate like the SiH4 was, but 8 coordinate. So how come if it's 8 coordinate is that its stoichiometry is still SiH4? That's because you have each silicon has 8 hydrogens around it, but each hydrogen is shared with 2 silicons. So it's SiH4 over H8 over 2, or SiH4. This is one structure. Someone else suggested a structure where which actually is of lower energy, where each silicon is surrounded by 8 silicons, but it shares 4 pairs of 2 hydrogens with each one in a structure like that of diborane. So actually, this is a part of the story. What is hard to get used to, it takes some time, is when you go from that structure, the silane, to the 8 coordinate structure, that nothing changes in terms of what is there. All that is happening is SiH4, taken an infinite number of times, is being squeezed. And in the smaller volume that is a unit cell of the squeezed SiH4, each silicon, it no longer forms 4 bonds, each with an electron pair. That's the way we describe silane or methane. Instead, it forms 8 bonds, but each with on average 1 electron in them. So that with increased density, with increasing pressure, you get higher coordination, you get more bonds, which of course must be partial since there are more of them. And they have the same number of electrons. Now, that situation, more bonds, same number of electrons. Hey, I've encountered that in chemistry before. I encountered it in my PhD work on the boron hydrides and the beautiful icosahedral structures of B12, H12, 2-. I've encountered it in the electron-rich bonding along the axis in what I usually call hypervalent molecules. I know how to deal with this as conceptually, and I do. Let me skip this for a moment because I'm going to be short on time. The next thing that happens after you do that, so when I say the next thing, I do not want you to think that this is A followed by B, followed by C, followed by D. I want you to think this is A overlapping with B, overlapping with C, overlapping with D as the pressure increases. So this is not a rigid hierarchy. This is a rough description of the physics and chemistry that happens. And what the next thing that happens is that you begin to decrease as you squeeze the length of covalent bonds and the size of anions. And eventually, new things begin to happen. You begin to move toward a plasma, is one way of saying it. Another way is that a new world of electrons moving off their atoms. There are new modes of correlation. I just want to show you the experimental facts because they are so impressive on their own. Here is what we have learned in the last 15 years, and which almost certainly does not appear in either your introductory chemistry or introductory physics textbook. Does not appear. So here's what we've learned. For every one of the alkali metal and alkaline earth parent structures, metallic, lithium, sodium, calcium, strontium, and so on, as you apply the pressure, they start out in close packed structures. That's what you learn in school. They are either face-centered cubic or hexagonal closest packed, or they are body-centered cubic, another popular type. And that's what they start out with. But when pressure is applied, they go into lower structures, and some of them are absolutely incredible. Let me give you two examples. In 1 atmosphere, barium, this is metallic barium, is body-centered cubic. I don't even draw the structures. You increase the pressure, it goes to face-centered cubic. No one is happy. No one's unhappy. It goes from 8 coordinates to 12 coordinates, so to speak. But at 25 GPa, it goes into a structure which has been determined by X-ray crystallography under the conditions of compression with 288 atoms in a unit cell. Why would it do that? That's an interesting question. Here's another one, rubidium, one of the alkali metals. It GPa, it goes in structure. 2 positions work. Incommensurate it's what a chemist might call an electrolyte. And this structure wasn't quite right, but then the experimental work from Nelms just 4 years later found that the general idea was right. The electrons go off the lithiums, which was the more important. This was a risky prediction, and it was wonderful that Neil Ashcroft found it. A very striking finding for the time. So what's happening? So why is this happening? So let's begin to talk about that. Why do things go out of close packing? So I'm going to take this slowly with you. First of all, since the beginning of civilization, and without waiting for scientists, people knew that the packing of identical spheres maximizes at 74%. You can do the calculation with spheres there is 26% left over in the holes in between. Whether you pack either hexagonal or cubic closest packing, either of the packing things where each atom has 12 neighbors, you can see the orange in the middle, 3 above, 3 below, and then 6 in the plane. So we have seen pictures in Egyptian wall paintings of stacks of fruit like this. People knew this was the closest packing, but it was not proven until about 15 years ago. People have done experiments with this. Here is from an early textbook of agricultural chemistry by Stephen Hales. A wonderful title, Vegetable Statics, or an account of some statical experiments on the sap in vegetables, being an essay toward the natural history of vegetation. Also an exact specimen of an attempt to analyze the air by a great variety of chemostatical experiments. Anyway, I reproduce what he wrote in the original old spelling. He took some peas. This is the old spelling. These are just normal peas that you'd get in a garden. He put them in a pot and he applied weights to it of 1,600, 800, and 400 pounds. In which experiments, though the peas dilated, yet they did not raise the lever, because what they increased in bulk was by the great, and he had no good way to say it. This is 1727, pressed into the interstices of the peas, which they adequately filled up, being thereby formed into pretty regular dodecahedrons. Let me translate that into modern English. It says, peas are not as stupid as people. If they are compressed, they will find a way to respond. And what they do in this case is they move into the space that is available. At least that's the simplest assumption. Turns out that close packing is not close enough. And now we go off on some other work, which has been done at NYU by Paul Chaikin. This is on the packing, not of spheres, but of M&Ms. M&Ms are little American candies that are the shape of ellipsoids, not spheres, but flattened spheres. Turns out that you can pack space more efficiently with ellipsoids than with spheres. In some way, you can understand it. If you take a bunch of coins and put them on top of each other, you are packing 100% in one dimension, but in the other two dimensions, you are packing like spheres. And the density overall of that array of coins is bigger than the array of spheres of the same diameter. There is another thing that people have found, not only that if you go away from spheres, you can pack more efficiently, but they found, and it's sort of obvious, that if you have spheres of unequal size, that you can pack more efficiently than if you have spheres of equal size. You can see this. There are these holes. You can fill up these holes if you have spheres which are of smaller diameter, in addition to the spheres that you have. So what is going on in this network over here is, again, the general principle that atoms and molecules are not as stupid as people. And what happens is, at some point, if you compress these, maybe a fraction of an electron jumps to one rubidium from another rubidium, making in the solid something which we can call rubidium plus, and part of it rubidium minus. And of course, rubidium plus will be smaller than rubidium minus, except this is a band picture, and this is not complete +1 and complete -1. But anyway, what you are doing by transferring an electron is forming two sublattices that could pack more tightly than the individual lattices. Then lattices of equal length. And also Neil Ashcroft's original suggestion about lithium had still another way, which is you take the electron off the atom and you put it in a hole between the atoms. And the packing of these electrides, which are essentially Li2 plus and an electron, the packing of these turns out to be very efficient. So this is another way. There have been theoretical investigations of sphere packings. It's clear that unequal spheres pack more easily. If you want to read more, look in our book here. In our book, our long article about the various things that determine. I wanted just to mention why I have here the chemical imagination. So let me talk about the title now. At work in very tight places is high pressure. And I showed you how that is done experimentally and theoretically. The chemical imagination, here I mean that things are suggested which come from chemistry and not necessarily from physics. For instance, that the bonding in this SiH8 has in it elements of bonding in diborane with two bridging hydrogens, and that it has electron deficient bonding in it. That's a very chemical idea. No solid state physicist knows about boron hydrides as a first approximation. It's a very chemical idea. For the rubidium structures, that you could, by transferring an electron to one, that you could form rubidium plus and rubidium minus, or partially that. And that anions are bigger than cations. That's again a very chemical idea. This was some suggested other structures for SiH4. If you are in the business of suggesting structures for a molecule, of course you use your chemical imagination. When I think of a structure for SiH4, I think naturally of CH4, but I also think of down group 14 from silicon to tin, germanium, and lead. And I think of tin tetrahydride, but I don't only think of tin tetrahydride. I also think of tin tetrafluoride, SnF4, because I'm a chemist. I know that, and see, this is a mapping that's not so obvious except to a chemist. I know that instead of hydrogen, I could put fluorine and get a similar molecule or other. Turns out that this is one of the structures of tin tetrafluoride with a 6 coordinates, with a 6 coordinate tin. And we suggested that as a structure for the silicon. So this is where the chemical comes in. I'm very happy to have been able to use my chemical experience in organic chemistry and inorganic chemistry in this realm of very high pressures. So I have told you everything I think I want to tell you. I just want to mention that, again, that many of these things will seem entirely new. That's because they are the subject of a lot of current research. From those superconductivities, which is like work done yesterday, to the structures of the alkali metals and alkaline earth, which is the last 15 years. They are entirely new. They're at the borderline of chemistry and physics. That's so obvious. But then I have chosen the problems to be at that borderline because I'm at that borderline in a number of ways. The other thing is that these are not very practical so far, except for making diamonds from graphite. They are experiments, but I have an underlying faith that part of the chemical imagination is, in fact, to turn basic science into things that are of possible commercial utility and also of value to humanity in other ways. I hope I have told you something new. That was my main goal. Thank you very much.
Thank you. Thank you very much for a great lecture. It was a big, very big pleasure for us to talk with you and to listen to you today. I have a few questions. Are these implications of atom squeezing at high pressure for process in Earth's interior?
Are they, I'm sorry, could you repeat your?
Yeah, of course. Are there implications of the atom squeezing at high pressure for processes in Earth's interior?
Yes, definitely. So the first thing to be said is we're in a curious stage of knowledge of our own planet. We have not been below a few kilometers by direct probing. And we do have incredible sophistication in probing of the Earth's interior indirectly, especially from volcanology, from knowing about the propagation of waves in various condensed media. We have a good idea of what is at the center of the Earth, but it's sort of interesting that we know more about the surface of Mars than we know about the interior of our own planet. We do have models for the interior, and there remain real mysteries. For instance, the core seems to be iron with a lot of nickel. There is some mysteries around the noble gases. Is there how much xenon and other gases is there in these admixtures? The work for things at high, chemistry at high pressure is driven in the work I've described to you, experimentally and theoretically, is driven very much by from one side, from geology and from what happens to materials under high pressure. It is also driven very much by planetology or astrochemistry or cosmochemistry, because we want to see how the planets are formed and what is their chemistry. There are so many, we know so many things, and yet we don't. There are many things we don't know. But yes, we know theoretically and from experimental studies a lot about what goes on in the interior of Earth.
Okay. All right. Can you tell some young scientists advices like how to become a scientist? Like, there's a big, hard path to do it. And maybe tell us something from your path, how you have become the scientist. Maybe it was from the school, how you have interested in it.
Yes, there are no there are no special clues or secrets or advices. One just tries to do as the best that one can. One tries to understand the world and to do so within the systems that form around us and the education we have. I'll tell you my own story. At least in outline, some of you may know it already. So I was born in Zolochiv in 1937. Zolochiv at the time was a town of about 12,000 people. It's a little bigger now. The population was around equally divided among Polish, Ukrainian, and Jewish ethnicities or communities. The educational institutions were largely Polish. There was for instance, the only secondary school in the town was the gymnasium was in Polish. My father was a civil engineer. I have some beautiful pictures of him from the Lvov, now the Polytechnic University, where he received his degree. My mother studied in Vienna. There was a lot of mobility between Austria and elsewhere. Also, my mother was by education a school teacher. 1937 was not in the end, it turned out to be not a good time to be born from someone from a Jewish background, because what we encountered was eventually the terrible obsession of the Nazis and their prejudice against the Jews. And that is by the end of the war, 1944. I'll tell you what happened in between a little bit. There were only 200 of the 4,000 Jews left in Zolochiv or Zolochiv. And many Ukrainians were killed, and many of the Poles were chased out. And that's a story that needs telling. The war broke out in 1939. I was 2 years old. We were under Soviet occupation, 39 to 41, a period that was for the Jewish population was not good for the Ukrainian population, because the Soviets viewed the Ukrainian population in our part as nationalists and treated them very badly. Anyway, 41, the Nazis invaded, and for us, a terrible period began in July 1941, around this time in 1941. And it did not end till we were liberated by the Red Army in June 1944, a period of 3 years. During that period, much of my family was killed, including my father. My mother and I and 2 uncles and an aunt survived in being hidden at the end of the war for 1.5 years in an attic of a schoolhouse in the village of Univ, not too far from Zolochiv. And we were hidden by a good Ukrainian family at great, great risk to their life. We have kept in touch with that family ever since. In 1944, we went back to Zolochiv for a short time. And it's at that point that I spoke Ukrainian. It was the street language. And I think I started school, but the system was not well set up. By December of 44, so that is a few months after we were freed and following the Red Army, we moved west and went to Poland, Przemysl first and then Krakow. And we lived in Poland in 1945. At this point, my last name, my first name, Roald, is what was given to me. I was named after a Norwegian explorer. We have no connections to Norway. Roald Amundsen, who was the first to reach the South Pole. I think my mother saw the name in a newspaper article. And my last name changed twice in that 1 year and a half. So when I was born as Roald Safran or Shafran. That was my father's name, Safran. And my father was killed in the war. Immediately after the war in Krakow, not immediately, within a year, my mother remarried a man who had lost his wife in the war. And I got a second last name, which was Margulius. And then on the way out of Poland, we bought some papers of a dead German soldier. We bought the papers in order to get in easier into the United States where we wanted to go. And those papers had the name Hoffmann. So that's the change in the three, in the names that I underwent. I went first to school in Krakow. We left in beginning of 1945 from Poland, wound up in refugee camps, which were not that bad, in Czechoslovakia, Austria, and Germany, until 4 years later, we finally got permission to travel to the United States, where we had relatives. I was, at this point, 11 years old. English was my sixth language. Nothing special about that. That's what happens with the refugees. No one asks you what school do you go to. You just go, you're put into whatever school there is. Different languages came, went. Eventually, I grew up in New York City, and my parents, as immigrants, and this is the typical immigrant experience, were never able to live up to their education or to practice what they were trained for, my stepfather and my mother. But for the children of that generation, the world was completely open, and the United States was, at that point, a very open society. I am very worried about the United States today. But at that time, the world was open to anyone who wanted to study. There was no question that one should study. I was the only child until I was 17, and then my sister was born. A brief summary of my university years at Columbia University is that I worked up enough courage. You have to understand the American system. American system, you get a general education first. You don't have to specialize. You don't go to medical school at age 18. You go to medical school after you finish the university at age 22, let's say. So I had a very good, what's called liberal arts education at Columbia. And during that, a brief summary of my education is I worked up enough courage by the time I was 21 to tell my parents that I did not want to become a doctor, okay? There was terrible family pressure to enter a profession. And I did not have enough courage to tell them I wanted to be an art historian. That would have killed them, I felt. So I settled on chemistry and went to graduate school in chemistry, doing very well in chemistry, but not sure about it. In fact, I did not make a commitment to chemistry until 3/4 of the way through my PhD in chemistry at Harvard University. Somewhere in that 3 years, I also went for a year to the Soviet Union on an exchange, not because I was a communist, but I think I was unsure about chemistry still. So I'm a latecomer to chemistry. And I also, my love for the humanities and the arts goes back to my university years. That's where I was exposed, and that has become, and that with time was an important guiding field for me for various psychological reasons, which we could talk about. But it turned out to be wonderful. And in 1 year, the last year of my PhD work, I really blossomed and became a theoretical chemist working with two people, Martin Guterman and William Lipscomb. And then I remained for 3 years at Harvard as a kind of independent researcher. That's when the work with Woodward that you know about, orbital symmetry, was developed. And after that, I began a career at Cornell University, where I have remained ever since. So that is a brief summary of my path. Now, what is to be learned from this? One is that, yes, it's important to come from a culture that values learning, and also it's important to be in a society which is open, which allows you the opportunities to do things that you want to do. There is something in here about, I think it's very important to be exposed to fields other than chemistry, and especially in my case, the humanities and the arts for scientists was very important. Maybe that was just me and nothing specific. I was following my nose, in a sense, just doing the next thing, making the compromises I needed in order to fulfill the needs of the family, always taking advantage of every opportunity that was to learn. That gives you an idea.
Thank you very much. That's very great support for us, and it's very important nowadays. Thank you for the great lecture, and also for after the lecture. Thank you very much. I guess that it will end very soon, and probably you will come to your motherland and maybe
yes,
and maybe give the lecture in person to our participants.
Yes, I would love to come again. I am getting old, but with luck, I will come again to Ukraine.
Thank you.
And may it be a peaceful land then.
Thank you very much. Have a good day.
Bye-bye.